Hello there, I'm Brás, a computer science doctoral student at the Federal University of Pelotas in Brazil, and I'm here today to talk about PACT, a citizen science project for computing education. We start with computational thinking. The expression is on the rise. It is featured in an increasing number of publications in the field of computer science and education. Among them are studies bringing technology to the classroom, programming, robotics, basic computer science, and general-purpose skills for problem-solving. There is a multitude of approaches and different answers to the main question: what is computational thinking? Given this situation, it was already suggested by previous researchers the creation of a centralized database for computational thinking resources. But if we take a closer look of what would be involved, we can see some promising opportunities. Professionals from different fields and even non-professionals work with computational thinking. That is an opportunity to build a bridge between these communities, allowing them to exchange experience and trade resources that would normally be restrained to their own community. We will focus on two groups: the researchers who study computational thinking in the backline, and the enthusiasts who apply computational thinking in the front line. While the enthusiasts can benefit from using tools and methods scientifically validated, the researchers could have access to way more data and experience reports to process their studies. This is the target of the project PACT, Partnership for Advancing Computational Thinking. It borrows the concept of citizen science, scientific studies with public participation. We highlight it doesn't mean putting citizens with no scientific training making careless studies. It is about enabling them to contribute to generate data that, in turn, will be analyzed by trained scientists. So, as computational thinking has multiple perspectives and we would be centralizing its resources, it is the ideal opportunity to confront, to compare and map all these different perspectives out there. The core idea is a three-layered database with generic classifications to organize resources that will relate to computational thinking subjects. Here comes the tricky part. We are not defining, describing, or organizing these subjects in the application layer. We are using an upper layer to organize and define the subjects according to the perspectives of each author. Because we need to float between modeling abstract and generic concepts such as the computational thinking skills, including abstraction itself, and concrete specific concepts such as educational resources like lesson plans and questionnaires, while trying to reach clear descriptions and even operate upon them to compare the perspectives, we came to the conclusion that ontologies would be a good fit for the job, since they can be described as shared explicit specifications of conceptualizations, and they can be used as shared vocabularies for integration and machine interpretable interoperation, which is just what we need to integrate the different perspectives and operate upon the vocabulary to find similarities, differences, and complements in those views. Ontologies have been used to represent knowledge across various areas, but on computational thinking, few applications were found, probably because ontologies look for standardizations and computational thinking brings various perspectives into play. This lack of standardization is indeed the main argument for related works to use a single author to define computational thinking. For instance, OntoScratch is an ontology for characterizing Scratch projects that uses inference rules to evaluate computational thinking skills involved in the given Scratch project. And this evaluation uses the same model or perspective of computational thinking of Dr. Scratch, an online tool that also evaluates Scratch projects. Another work that uses an ontology for computational thinking is MAKEUS, that categorizes computational thinking learning resources by area and school year, being the base for a web platform for searching these resources. That is pretty close to one of the purposes of PACT. Yet, MAKEUS also uses only one view of computational thinking, provided by Computing at School from Barefoot Computing. Therefore, we present PACT, the ontology that paves the way for the PACT project. Its main distinction from previous works is the ability to integrate different authors' views, models, and definitions of computational thinking, and also the purpose to bridge different communities. In order to show the modeling capabilities of Unplugged, we instantiated the views of three different authors on computational thinking: Janet Wing, Brennan and Hasnick, and Silva Jr., that would be me by the way, as well as three different examples of resources that could be stored in the database: the computational thinking test, a computer science unplugged activity, and a Scratch project. The first author we selected was Janet Wing due to its influence in the area, but she never conceptualized a model of computational thinking. Her papers are discursive. She argues about the importance of computational thinking and how it's present in everyday life of citizens in general. So we built a model for her based on her top 2 most cited papers. We gathered her descriptions of computational thinking and related processes, simplifying them into elements and relations for the ontology. The second author is actually 2, Karen Brennan and Mitchell Resnick. They were selected because they built a model of computational thinking for a specific purpose, Scratch programming, and also because their work is one of the most cited within the field. They described computational thinking as having 3 key dimensions: concepts, practices, and perspectives. As they built an actual model, contrary to Wing, we just took their model as it is. The third author was selected because his model comes from a systematic literature review, aiming to be more generic and cover more. Also taking the model as is, it groups several concepts into what it calls the lines of computational thinking: abstraction, decomposition, algorithms, data, automation, and evaluation. Now, for the ontology, as it is meant to enable the PACT project, it should be fit for web platforms. Thus, we developed it looking for the integration with the semantic web. So, Unplugged was created using the web ontology language that defines all vocabulary classes as subclasses of thing, and we built it through the framework Protégé. The implementation of the perspective layer was made using high-level ontologies, one for each author. These ontologies are, in turn, imported into a low-level ontology that models the application layer. At last, the files of the example resources in a database constitutes the instance layer. The high-level ontologies are unique for each author, but the low-level ontology has the following structures. As computational thinking revolves around problem solving, we start with a problem that requires a solution that may be reached with the help of a subject that may be approached by a resource. Just to make it clear, these relations are end-to-end. It could be 0, 1, or more. There are several subjects, but they are not organized in any way in the lower level ontology. On the other hand, the resources have a hierarchy of classifications. And to be able to explore these resources more specifically, we split them into fragments. So I can model as a resource the computational thinking test as a whole, but also model each of its questions as a separated fragment. At last, each of these fragments materializes a task. We have considered this class to highlight that activities and questions from different resources sometimes expects the student to do the same thing, just in different contexts. So it could be useful to track and even recommend similar activities and resources. Moving on to our case study, we have modeled the computational thinking test, an online exam with closed-ended questions about things like algorithms, conditionals, loops, functions, and debugging. Furthermore, we have modeled some samples of its questions by analyzing the specific question in the online test. The computer science unplugged activity was KidsBot, where students programmed directions for others to follow as they were robots. We modeled as fragments of it samples of the steps presented in the website to guide the activity. The Scratch project was cats, the making of a never-ending flow of walking cats that you can help by drawing bridges and walls. We also added as fragments of the respective resources the materials required by them, such as cats requiring a computer since it's a virtual activity, and KidsBots requiring something to write down the commanded directions. Each of these fragments approaches one or more subjects. As we can see, algorithm is a highly approached subject in the samples, while remixing is touched by only one fragment. Not shown here, but each of these fragments materializes a task, as we've mentioned before. And with these samples, the task of making a path by repeating direction showed up in all three resources, just varying its form, as a multiple choice question, as an outside activity, and as a block programming function. For the multiple perspectives, our case study shows the intersections and differences through the subjects approached by those resources. While Wing says abstraction is the essence of computational thinking, Brennan and Resnick says it is a computational thinking practice, and Silva Jr. says it is one of the 6 computational thinking lines. As this algorithm, that is, for this author, both concepts are in the same hierarchical level, but for Wing, algorithm is an abstraction of a process. She doesn't consider an hierarchical organization at all. What is interesting to note is that although they are different perspectives, they do not necessarily deny or conflict each other. You could say abstraction is the essence of computational thinking and is a practice and is a computational thinking line. Thus, we presented PACT, a project to bridge researchers and enthusiasts of computational thinking, granting, on one hand, the scientific assurance to the tools and methods the enthusiasts use, and, on the other hand, the data and experience reports of the enthusiasts to researchers to complement the data gathered in a small controlled experiment, following the citizen science logic. Then, we present the implementation of this project, the Pact, a multi-layered ontology that models computational thinking resources while allowing multiple perspectives of computational thinking to be considered in relation to the subjects approached in those resources. Pact shows the capabilities to integrate and analyze views of different authors, what is not just an innovation in the computational thinking, but also remarkable for ontologies as well, since they usually rely on consensus of specialists of the domain of knowledge. Making use of the perspective layer of Pact, we intend to map and analyze the views of more computational thinking authors and open for public editions of perspectives. For the PACT project, the next step is to build the database using the Pact. Then make it public and populate the repository. And that's all. Thank you very much, and I'm open for questions.